Cool. Well, thanks for being here guys. That's cool that I'm kicking off this session. So I'll talk about PiecewiseInference.jl, which is a library I've been working on. Ah, can't you? You can't see anything? Okay. How about that? No? It was... Okay. And if I do something like that, so that I have the time, does it work still? Awesome. Cool. Yeah. So PiecewiseInference.jl, which is a framework, framework for inverse modeling with time series. So the motivation for this project was that I had the differential equation model, which had chaotic dynamics, and I wanted to fit it against data. So the amazing thing about SciML is that you can, write a loss function that you define as the distance between model outputs and the data, and then you can use gradient-based methods to minimize this function to find the parameters that best explain the data, which is great because those gradient-based methods are very efficient. But no matter how hard I would try, I would always end up with like this kind of bad convergence behavior, where the loss function for some parameters is undefined because the model just throws nans for those parameter values. Then I would observe always, huge gaps in the loss function, and then actually when you look at the fit, the result of the fit, it was always pretty bad. So very bad estimate of parameters. So that's why I started thinking of strategies to improve the convergence of these gradient-based methods when using them for mechanistic models. And I came up with this PiecewiseInference.jl, which kind of really smoothens the whole convergence, the convergence of smoothens the loss landscape and improves the convergence of gradient-based methods. So there's a bunch of strategies involved here. The first one is segmentation. It's kind of another flavor of multiple shooting, where basically instead of trying to fit the model on the full length time series, we break down the problem and only try to fit the model on independent partitions of the time series. And this breaks down the complexity. Actually, the model tends to diverge. The divergence of the model tends to increase actually exponentially if you have a chaotic model over time. So by limiting the time horizon, you smoothen basically the loss landscape. And not only do we do this, but we actually infer the initial conditions on each of those partitions. And this has two advantages. Well, the first one is that your data is usually contaminated with noise. And if you have a chaotic model, then the mismatch between the initial condition and the data and the true state, this mismatch is going to contaminate your prediction and exponentially increase over time. And so by trying to best match the true state, you reduce this problem. And then the second cool thing is that it allows you to have a model which has a higher number of state variables than the data that you have for, so that you can basically model latent variables, etc., which was very useful in my case. Now the second strategy is minibatching. This is something that is very commonly used in the machine learning world, but not so much when fitting mechanistic models. So it's basically about instead of trying to fit all the batches at one time for the parameter update, you only take a random subset of those partitions. And this has two advantages. The first one is that it introduces randomness into the fitting process, so that you can get out of local minima. And the second advantage is that it may increase the inference time by reducing basically the augmented parameter vector by removing some initial conditions that you need to infer for this specific batch. Right, and the second strategy is pretty simple. We use bijectors.jl to define the region in the parameter space which is valid for the model, and then we map this region into an optimization space which is real valued, where the gradient-based method can do its updates on the parameters, and then we map back this real valued optimization space into the valid parameter space. So I'll just walk you through a quick example. using PiecewiseInference.jl to infer the R and B parameter of this population growth model. So essentially, you need to define your model in a specific way, which is kind of a PyTorch approach, where you need to register your model, and then you would define the equations similarly to what you would do with differential equations.jl. But then you would have this to construct this variable, which takes in all the relevant parameters for your numerical simulation, so that you don't have to worry about this later on. And you can call these simulate functions to simulate your model with different parameters, inputs, etc. So this is actually useful besides PiecewiseInference.jl, but it's also used in the internals. Now, once you've defined your model, you need to define an inference problem with an initial guess for the parameters and those bijectors that I was talking about, as well as custom loss functions. And finally, you can call the main function of PiecewiseInference.jl, which is this inference function. And here, the critical meta parameter is the segment size, which will critically affect the performance of the inference. What do I mean by this? So basically, this is a benchmark that we did on several mechanistic models. So these are ecosystem models. I'm working in biology, ecology actually, where each of those diagram stands for a particular model with a higher number of, with an increasing number of state variables. Here with 7 state variables, which corresponds to biological species. Anyways, and so you can see that in all those models, all those tests, there is a sweet spot for the segment size, and this is related to the fact that when you decrease the segment size, you tend to smoothen the loss landscape. So this is great for convergence, but essentially you're going to lose some information on the parameter constraint. And so to find this sweet spot, the best way is to use cross-validation, basically. Another thing that you can observe in this graph is in these diagrams is like, so the colors here stand for different levels of noise that we artificially put into the data. And so you can see that the model is actually, the method is quite robust against noise. And this is thanks to the fact that we infer the initial conditions. Right, so additional features, we support not only differential equation-based models, but also discrete models, discrete maps, sorry, here is the logistic map, the logistic discrete map, and we also support like any analytical function which takes time as an argument. In fact, we're working on a manuscript where we use the method for fitting autoregressive neural networks, and we show that it works great actually in this specific case as well. Now, future plans are, well, I think the interface with the definition of the model, separating the model parameters from the model definition is nice, and the idea, my vision here is to actually provide utilities so that the inference is more statistically robust by providing, for example, the Akaike information score for the model, and something that I would really care about also is like to provide estimates of the error for the parameters, which we can get from the Fisher information matrix and all sorts of other tricks. So yeah, I won't have time to go into that. Thank you for your attention. I'm very happy to take any questions.
We're going to answer questions while switching my microphone over here.